Hey everyone, we are looking at radioactivity today, and by the end of this lesson, you should be able to explain the process of radioactive decay by the use of nuclear equations. I know this says and half-life, but that'll be the next lesson. So let's talk about radioactive decay. So decay is a random event, and it is independent of energy influences. So it will just happen. You don't have to put energy in to make this happen. It will happen on its own. I mean, energy might make it happen a little bit more, but still random. And some definitions for you to look at here are parent atom. This is known as your original atom or the reactant, which means it's what you start with. And this is the opposite side of your decay particle. So this will be on the left side. Your decay particle will show up on the right side. And then you have your daughter atom, which is what you produce. So that's your product. This will be on the same side as your decay particle because your decay particle is released with the daughter. And then I just put Madame Curie over here because she was known for studying radioactive materials. So now let's talk about our three decay particles that you need to know for nuclear equations. The first one is alpha decay. Its symbol is this little sideways fish, and its notation in a nuclear decay equation is a helium particle. And the reason it's a helium particle is because it gives off 2 neutrons and 2 protons. Since it gives off 2 protons, this does have a +2 charge, and it means it has an atomic number of 2 and a mass number of 4, which is what helium looks like. So you would note this as a helium atom. This is our weakest form of decay, and that is shown by the fact that it is stopped by paper. Atomic number of your parent atom will decrease by 2, and mass number will decrease by 4. So your daughter atom will be smaller by those measurements. Our next one is beta decay, and it's this capital B with a tail, and it's noted in a nuclear equation for you guys. It can actually be noted a couple ways, but for you guys, it'll be like an electron. So remember, an electron has no mass that we register, but it does have an atomic number, quote unquote, of -1 because it has a -1 charge. This is due to an electron being ejected from the nucleus. And actually, this should say neutron. So I'm going to kind of write that here. So from a neutron. Because a neutron can be thought of as a proton and electron hooked together, matched together. And if you get rid of an electron, that means you have one more proton in your atom or in your nucleus. So your atomic number should increase by 1 from parent to daughter. And this can be stopped by aluminum or wood. So I compare these to an alpha decay particle is like a wiffle ball. So, if you've ever been hit by one of those, it doesn't hurt that bad. It slows down because of air. But beta decay or beta particle is more like a BB. So if you've ever been hit by a BB out of a BB gun, it hurts really bad. So this can be stopped by stronger materials. And then our last one is a gamma ray. And a gamma ray has no mass and no charge. So it looks like this. I don't know why my symbol's not here. It's like this little funny looking Y with 2 zeros because it has no mass and no charge. It's also a high energy wave. So since it's a high energy wave, it tends to be given off with some other type of decay. So it's given off with alpha or with beta. And then it's slowed down, not stopped, but slowed down by lead or concrete. And I'm pretty sure it's 6 feet of lead or 10 feet of concrete will slow this down. That shows how strong this type of decay is. And, if it makes any difference here for you, remember, gamma radiation is what made the Hulk. And the reason being is because it's such a strong type of decay. So this little picture here shows you how your particles can be stopped, okay, and what they're stopped by. Oh, let me clear this off, sorry. So now let's talk about nuclear decay equations for these. So this shows the parent, daughter, and the type of decay that occurs, written as like a chemical equation. You have to balance both sides, which means you have to make sure the top numbers are equal on both sides of the arrow and the bottom numbers are equal on both sides of the arrow. If elements are on opposite sides of the arrow, you will subtract the top numbers and subtract the bottom numbers. If they're on the same side of the arrow, you add the top numbers and add the bottom numbers. So here's a picture just to show you of what a nuclear decay equation looks like. So we've got our parent atoms on the left, we've got our daughter atoms on the right, as well as the decay that was produced. A lot of times you'll know the parent atom, I'll tell you what type of decay comes out, and then you have to subtract these numbers to figure out what daughter atom is. Or I'll give you the parent and the daughter, and then you tell me what type of decay occurs. Okay? Or I'll give you the daughter and the decay, and you tell me what was the parent atom. So when you look at these, like let's say you didn't know this one, so let's scribble that out for a second, and you want to figure out what the daughter atom is. You will take these top numbers and you will subtract them. You will take these bottom numbers and you will subtract them. So 238 minus 4 is 234. And then 92 minus 2 is 90. And remember, you use this number, the atomic number, to tell you what the new element is. And you would just write it like that. So let's say we didn't know this one. Okay? These two are on the same side, so you're going to take these and you're going to add them. And you're going to take these and you're going to add them. Which will be 234 plus 0, so that's 234. 91 plus a negative 1 would be 90. And again, use that bottom number to figure out your element. Okay, it's pretty easy. It's not hard at all. And you're given everything but one of these to solve for. So down here just shows you what this actually looks like. So you give off a helium and you're left with thorium. Remember, we said that you don't change elements, right? Elements retain their identity. This is the only time you're going to change elements, and it's because you're changing the protons in that nucleus. We said if you change the protons, you're changing the element you're looking at, and that's what's happening here. So changing protons is all due to nuclear chemistry. So let's go ahead and let's try this example, and it's one we just literally just looked at. So what's the daughter atom? I've given you the parent. I've given you the type of decay. We subtract the tops and bottoms on both sides since they're on opposite sides of this arrow, and determine the element using the atomic number, which would be 90, and that's going to be thorium. Both sides of your equation must equal, so that means you got to balance these top numbers and balance the bottom numbers. So 234 plus 4 is equal to 238. That's good. 90 plus 2 is equal to 92. That's good. So now I want you to try this one, and you have to determine the type of decay that occurs here. Okay. So pause the video and try that. All right, guys, we have finished this video, so hopefully now you can